Yesterday we finished with that r equals 2 sine of 3 theta. And kind of right at the end, I think you guys noticed kind of an important thing that for that particular rose, r equals 2 sine of 3 theta, the domain to get the whole graph was actually maybe unexpected, right? 0 to 2 pi seems pretty standard with a lot of these, but as you can see, I've still got that up on my calculator. We were able to complete the entire rows in just 0 to 1 pi instead of 0 to 2 pi. And we didn't really have time to explore much beyond that. But the next one over there, r is equal to 3 cosine of 2 theta. Hopefully you got to a point where you graphed that. It looks pretty different, right? So let's maybe point out some similarities and differences. So for example, when you have r equals 2 sine of 3 theta, all you really have to do is just look over here. Whoops. Just look over here, and you can see that that rose has how many petals? Do you see any connection there with the equation that generated the graph?
3 theta.
3 theta, right? So you see 3 theta, it seems to go along with 3 petals on the flower, on the rose. Okay. But maybe, I don't know, maybe you noticed a little issue with that pattern when you graph the next one. So I'll graph that one real quick. So if I go r equals, instead of 2 sine of 3 theta, I'll go 3 cosine of 2 theta. I think some interesting things happen. So you graph this, and I don't know what you had your calculator set on, but I can see this. Can you see how I only have part of the flower graph, part of the roses up there? So if you remember from yesterday, I had this left over. My window, for my theta range, my theta went from 0 to pi. And so if you go back to the graph, you can see that it appears, at least, from what we would expect to happen, 0 to pi is not enough theta for us to get the whole graph. So it's a little bit different than the other one. So I go back. What would you guys guess would be enough theta to get the entire graph, but not more than the entire graph? 2 pi. Okay, so let's try that. 2 pi. And we hit graph. And you can see that 2 pi going all the way through. And you can see that blue circle completes its full 2 pi revolution right at the same time that the rose finishes its graph, right? What's interesting about this is you guys did a great job, guessing the appropriate theta, 0 to 2 pi. If you were bad guessers and you said, you know what, I think instead of 0 to 2 pi, it should be 0 to like 6 pi. Let's think about what that would do. Maybe help us see this. I'm going to change our graph look a little bit. We're going to go with that. So check this out. So would you guys agree 0 to 6 pi is way too much? So let's just watch what happens when I graph this. So hit graph, you can see that rose being traced, and right there at 2 pi it's enough. But if I keep going, what happens? It just keeps on following the path, like the little dot you can see, and eventually it gets to the end, right? Okay, so there's certainly going to be kind of a caution or a danger here that we'll want to take a look at that arises when you trace the graph too many times or not enough. It's going to be an issue, okay? So this one, 0 to 2 pi was enough, and we would leave it at that. Did you also notice that pattern with the number of petals on the rose is different? Remember with this one, it was sine of 3 theta, and that gave us 3 petals on the rose. Over here, it's cosine of 2 theta, and I don't have it's not a 2-petaled rose. It's 4. A little bit different, right? Maybe unexpected. We'll try to draw some conclusions. Okay, and then what was the last one? I forget. 2 sine of 5 theta. Okay, so let's take a look at that. I just need to come back over here and go 2 sine of 5 theta. And I'll go back to, what do you guys think as far as domain on this one? Should I go, I think 6 pi probably we would accept is probably too much. But what do you think? 0 to 2 pi? 0 to 2 pi. So let's go 0 to 2 pi. And we hit graph. We can see our circle going. What do you see happening? Too much. So let's go back and change the timing a little bit and see if we can notice by how much too much. So check this out again. Did you see it? It's kind of hard to see. It's still sort of fast. 3 pi over 2, okay. So let's see here. Let's go window, and I'll change this to be 3 pi over dos. Are you watching? You got to watch. It happens sort of quick. Let's see if this is just right, not enough, or too much. Say again? Just pi? Okay, let's try that. Obviously, we're decreasing this because we can see that it's a little too much. So 0 to pi. Hit graph again. Watching carefully. That's it, isn't it? Like at that point, you can see the blue circle is traced 0 to pi radians. And what we'd expect perhaps the rows to look like is all there. Interesting, right? So have you drawn any connections about these roses yet as far as how the numbers and the number of petals and the domain and all that stuff work out? Any conclusions? So if n is odd, right, the number attached to the theta?
0 pi.
Yeah, that's it. You guys have come to a good conclusion, I think. I'll say it out loud again in case maybe you didn't hear. If n is odd, so in other words, like 2 sine of 3 pi or 2 sine of 5 pi, I think is the one we just did, then if that number attached to the coefficient of theta is odd, then you only need 0 to pi to make the whole rows. And the number of petals will match that odd coefficient. So then what's the counter to that with the r equals 3 cosine of 2 theta? Yeah, it's double, right? Yeah, so if the coefficient is 2, you're going to get 4 petals. If n happened to be like 6, like 3 sine of 6 pi or theta, something like that, then you'd have 12. Lots of them, right? And what kind of a domain do you need if your n is even? 0 to 2 pi. Okay, so there's some important connections to make. But again, I don't know. I think these are handy to have in your mind, but it's not like, bless you, it's not like I'm going to quiz you on that and say, hey, n is odd. How many flowers on the rose? It's more about understanding when the petals start and stop and how many petals there are and trying to put that together versus just like this strict memorization. A big takeaway here would be this. Whether n is even or odd or whatever, where do all of the petals on the rows start and stop? At the origin. That's a really big takeaway, right? So as I mentioned the other day, there are going to be times when the question is going to be, hey, let's find the area within one of the petals of the rose. It's going to be really key that you know that the petals of the rose start and stop at the origin. Right? And at the origin, how long is the radius? It's 0. Right? So those connections are going to be very important as far as establishing, how do I even set this thing up? Once you set it up, I think it's either going to be a calculator active or a very straightforward scenario, but it's the setting of it up that sometimes is problematic. All right. So do you guys have any questions? We've got a little more to do here. Doing all right? Yeah.
Will the number of petals or anything depend on sine or cosine?
The orientation of it, yes, but not the number of petals. Yeah. Good question. Anybody else? All right. Fair enough. So then, if you have not already looked at the last 3 graphs there, please do. Use your calculator. Again, go ahead and graph those. Get the graphs traced onto your paper there. Do some thinking about it. But I think just as important, maybe more important, is playing around with these things. I really honestly advocate that, right? Just mess around with it and think, well, gosh, what if I just added this in there? Or what if I threw an e to the something in there? What would that do? Blah, blah, blah. I think you can start to figure out some interesting things, or at least have some good questions if you start just playing around. Okay to do. So 1 plus 2 cosine of theta is, there we go. There we go, that's it. You can see that this is, I guess it's a little bit off the side there. This is not going to be totally graphed with just 0 to pi, right? You see, it appears at least that we have part of it, but not all of it. What did you guys come up with for an appropriate domain to get the whole thing? 2 pi, I think, is right. So window, instead of 0 to pi, goes 0 to 2 pi. And we hopefully get the whole thing graphed. I think that you'll see this is one of those looped limicons or limicons. It's certainly not a Lanechan or whatever. I don't know. Otherwise, we could butcher the way we say that. You can see that it takes 2 pi for it to get all the way through its full graph. And like I mentioned, I think the other day, we'll do all kinds of things with this. We could, for instance, find the area within the little tiny loop in there. You could also find, certainly this would be a little more challenging, you could find all the area that's inside the big loop, yet not inside the little loop. Right? So there's all kinds of ways you could do that. Do you see how, for most of these, maybe if not, you can't really say all of them. I can think of a counterexample for sure. But for most of these, can you see how symmetry could very easily have a very positive effect on how you'd approach it? So consider, might be something that would save you time, effort, energy, so on and so forth. Okay, so that's a looped limicon. And then we've got the French version, yes. Oh, come on. There we go. And then, of course, we've got the 2 plus 2 sine of theta. And can you guys see, you probably noticed this already, that this next one, doesn't it look almost like a looped limicon that tried to be a looped limicon but didn't quite make it? You see how it was like trying to? Here, we'll look at it here. You can kind of see how it was trying really hard to be a looped limicon. Like right about here, it was going to... it didn't. Right? So close. It was going to go and... no, it didn't. It just kind of turned around right there. And can you see how it's a pretty sharp turnaround point? It doesn't really appear to be one of those smooth ones where tangent, slope of tangent is 0. It does appear to be the proverbial sharp point. So again, something like this, we could easily look at this from a calculus perspective and ask the question of area. We could also ask the question of where is the slope 0? Where is there a horizontal tangent? Where is there a vertical tangent? So let me ask you that. Just looking at the red graph right there, how many different horizontal tangents would you guess would be there for this? Say again? 3? Okay, so let's see here. Let's draw them in. One of them pretty obvious right there, right? There's one. And where would the other one or other ones be? Horizontal tangents? So kind of like, well, I think you're thinking vertical, Jasmine. So I'm thinking horizontal would be down here on the bottom.
Would that just be one horizontal tangent?
So from the perspective of the equation of it, I think so. By symmetry, it looks like it's at about the same vertical place. But from an angle perspective, there'd be 2 different angles that would cause a horizontal tangent. But in the end, the equation for those horizontal tangents would be the same equation. I think so. What about vertical tangents? Do you guys see any of those on the graph like this? 2 of them, and they're on the sides. So Vertical tangent, or right about there. Another one right, that's not very vertical, but you get the...
What about that little point at the pole?
So the point right there at the pole, the sharp point right there, I think we would end up finding out that that literally is a sharp point. That the tangent line would just not exist there. There would be no one tangent line you could draw there because of the instantaneous change in slope. Say again? The doink point, yes. That's it. Okay. Guys, questions, concerns at all about looped limacons? This is called a cardioid, which is a version of a limason, more or less. There's also the dimpled limason. The dimpled limason is even more of a failure in the perspective of it's trying to loop back, but then it doesn't even get to a sharp point. It just sort of like, it doesn't even make it. So, anyhow. Any follow-ups or clarifying questions on any of that? And does anybody know the name of the very last graph that I've got listed up there? The R squared. It's a lemniscate. Yes, lemniscate. Okay, did you guys have to graph the lemniscate in two parts?
Yes.
You do, right, because of the R squared. There's no opportunity to have an output of R squared. So if we graph that, it would be 3, or I guess you could just go square root of 9 cosine 2 theta. When you graph this part, you can kind of see that it gets pieces of it, right? I did the whole 2 theta. Why am I missing chunks out of the middle? Say again? Step size is too big, right? So I'm not dropping enough breadcrumbs. So I could go back into here and say, instead of 0.09, I don't know, 0.04 make much of a difference? I don't know where you guys went with this. Hey, that made a pretty good difference. It's pretty close. Yeah, almost. Lacking a little symmetry there. I think it's more of a technology issue than anything else. Let's see here. Let me do one more, and I'll have a question for you. So 0.02, how about it? I want you guys to pay really close attention. I want you to notice something about this graph, and we'll try to figure out why it's doing what it's doing. So please watch the timing. So I still have that blue circle up there, kind of like a clock, telling us theta is progressing, right? But I want you to notice something about the red graph while that's happening. So here we go. Blue circle's going. It's going very slow here. Notice, I don't know, what do you notice? So the red graph just moving along. Okay, I think that's a pretty good demonstration. So what did you guys notice? The blue graph did its thing. Certainly seemed to pause, right? Then there certainly seemed to be times when blue just continued along its merry way, but the red just, like you said, paused. And you were trying to identify like what angles were the pauses happening, right? It's good, it's good. Why on earth would the red graph pause? Because it was. It definitely was. Like what's causing that? What do you think? Yeah. So, in other words, wherever 9 cosine of 2 theta, was it 2 theta? Yeah. 9 cosine of 2 theta, wherever that was negative, you're not going to get any radii because you're going to be doing the square root of a negative. It's just going to be sitting there saying, not a real number, not a real number, real numbers again. It'll start plotting some radius as we go, some radii, and you'll get to some more places where the input for the square root's negative, and it'll pause, and I don't graph, we don't graph imaginary numbers, at least on this, on a real graph. And then it would pick it up again. That makes sense? And so that's where you get these lemniscates. Looks like an 8. So a sideways 8, like an infinity. Maybe one other question, follow up here. This was 9 cosine of 2 theta, right? And obviously it was a kind of an infinity symbol. what is the one thing that I would need to change about the equation to change this lemniscate from looking like an infinity symbol to an 8? Instead of cosine, sine. That's right. So again, just in the spirit of playing around with this, let's confirm. So instead of cosine, now it's sine. We graph this. And we see the pausing happening. And then we see it starting again. And this is where it's a little unexpected. It's actually, it's just a 45-degree looking angle, right? Instead of the full 90-degree shift. And obviously I've got some work to do with my step size to get to the complete graph. So maybe, golly, 0.02 is already pretty small. 0.009, it's going to take forever, but we can just chat while we're there. Okay. So I think, especially when you are first learning about graphs, or maybe just refreshing your memory about graphs, messing around with it is sometimes the best thing to do because you start to come up with these curious qualities. Like Dylan came up with this crazy graph that involved a square root and an e and a tangent and a natural log and some combination. And we were looking at the graph and questioning, well, why does this show up here? And what does that mean about this? And blah, blah, blah. And I think it brings up some good questions. So, I mean, you guys are all creative people. I'm sure you can come up with these insanely crazy graphs that, or a 700-petaled flower or whatever that was, You can do all kinds of stuff like that. But if your goal is to try to explore and learn and mess around and be like, whoa, what does this mean? Or why does it do that? I think it's all good effort in a quest to gain some understanding. So, anyway, man, that didn't even help that much, did it? Oh, it did? I wasn't paying attention. Okay. Lemniscates. So we'll do a little more exploring with those later. But for now, that's good enough. All right, so then down here below, I think, I've got a couple of questions here. And I think we've talked about a lot of these. I wanted to just make sure that we put these in here just to make sure I didn't forget to talk about them. I think we've done this. You guys, so let's just make this sort of a mental checklist. Are you guys okay playing with the domain? 0 to 2 pi, 0 to pi, what that may or may not do with a graph. So think about what that is. What happens with roses when n is either even or odd? How does that change things? And then the last one there, we certainly talked about understanding where a graph starts and stops, how the origin of the pole functions into a graph, and the importance of not overtracing it. We've talked a little bit about area. Can you imagine if you overtrace the graph, isn't the integral just going to do whatever you told it to do? And if you tell it to accumulate area over too big of a domain, guess what it's going to do? It's just going to keep accumulating area, and your area will be like twice as big as it should be, or 1.5 times bigger than it should be, or whatever the case might be. So you want to be very careful that you we're safe with that. And then maybe a last thought about maybe even say like the roses. What would be a strategy you would take? What if we had like some 5-petaled rose like we had earlier? What if I said, what's the area within the whole rose? What might you do? 1 petal times 5. Yeah. Use symmetry to your advantage. All those old rules, all those old concepts and strategies that we've used with other areas and volumes and things, I think come into play here too. Okay. So I am about to do a little transition. We've got about 18 minutes left. We are not going to be in any kind of a rush here, but I'm going to transition a little bit from what for the last couple of days more or less has just been about pre-calculus. And we're going to transition a little bit into calculus today. Unless you have any follow-up questions about polar graphs. So before we move on, let me just phrase it like this. Before Tuesday, we had a very mixed bag in this class as far as polar graphs. There are some people in this class that had it in DC pre-calculus, and though they might have been a little bit rusty, at one point they were at least decent at it, right? There are some other folks that were in DC pre-calc that maybe that was the one unit where you're just like, what? And you never really got it. and you still weren't really feeling like you had it before Tuesday. And there are other people that didn't have a course that covered polar, and you had never even heard of it before. When you heard the word polar, you just thought that that means it was cold outside, or the North Pole on the Earth or something, right? So my goal for the last class and a half or so has been to even the playing field as much as possible. Does that make sense? So for those that were rusty, maybe you're less rusty. For those that were decent at it before, you're still good. For those that never saw it before, you're starting to be like, oh, okay, it's just angles and radii, and we can make all these different graphs. I mean, that's kind of the hope. How are you feeling? Let's take it. Less rusty? Okay, that's good. That's good. I think you have an advantage in the fact that the main thing here isn't like all the nitty-gritty like rules about polar graphs. Like I think Jaden was asking about, or Colin maybe about, do we have to know this and that about polar graphs? And I totally get that. There's a lot to memorize. It's not really about that. We're going to be focusing on what can we do with calculus. Okay. So here's my segue. And I think this is good timing because I was just messing with this, and Jaden brought it up. I think others know this too. Your theta step makes a big difference on getting a complete picture or lack thereof for a graph, right? The theta step. Yes, no? Okay, I mean, let me just give you an example. Let me go back to this real quick. If I go back to my window, instead of my theta step being 0.009, what if I just made it like 1? Check this out. Let's see what happens. I have no idea what's going to happen. Look. Very different, right? So all of a sudden my circle becomes like a 1, 2, 3, sort of an incomplete hexagon. And what I know to be a lemniscate just appears to be a line segment. Huh, interesting. And we could be even sillier with it. What if my theta step was 2? Is anything even going to show up? Oh, it's a triangle now. When the lemniscate sort of showed up and then disappeared. And of course, the counter to this is what if my theta step was a bunch of zeros and a 1? This is going to take forever. It's going to take, oh, okay. Apparently two forever. So let's adjust our way of thinking here. And let's just go 0.3 zeros in a 1. Maybe that'll work. Okay, that's going to work. Very slow. So while this is attempting to do its, you can see it moving. It is moving, but it's very slow. Where have you guys seen the concept of a theta step? It wasn't exactly worded that way, but it was spiritual. T-step. Where did we do the T-step? Okay. Oh, you're thinking of, okay, you're thinking of step size. And that was like the little jump into X that we did, and that's actually pretty much similar. I'm thinking of something a little more contained, something a little just. But you're right, that is like very similar. Parametric and that. Right? Remember how we had the same idea with parametric and vector? If we mess with the T-step, we got similar looking to your graph. Like you can take something that clearly is supposed to be curving and turn it into a hexagon or a triangle or whatever. So guys, here's the big transition. This, I hope will be very helpful for you. Polar graphs, polar equations are nothing more than parametric. They're just parametric. The difference is with parametric, the classic ones we did before, the parameter was time. Like X depended on time, Y depended on time. Right? So these polar graphs are parametric, and you're going to find that X doesn't depend on the time really in the same sense, and Y does not depend on time in the same sense. What do you guys guess X and Y would depend on? Theta for sure, and you could sort of say R also, but R is usually in terms of theta, so technically really they would just be in terms of theta. So theta will function almost like our time. And I hope that you notice, like with that blue circle that I had on all these graphs, that functioned like our clock, right? It would go all the way around. Sometimes it took 12 hours or 2 pi to get all the way around our graph. Sometimes it only took 6 hours, aka 1 pi, to get all the way around our graph. So theta will kind of function as a time. And of course, when you make your theta step really tiny, effectively, what are you doing to the time? Say again? I'm listening for anything. I'm just hearing like little secret things. It takes forever, so what's it doing to time? Remember with parametric, I told you the t-step was kind of like the how often do you drop a breadcrumb on the ground? And so when your t-step is really tiny, you're dropping lots of breadcrumbs, which means you're going to have to reach into your bag of breadcrumbs a lot. That's why it's really slow. If you're dropping a breadcrumb every foot, boom, 1 foot, drop one, 1 foot, drop one. That's a lot faster than if you're dropping a breadcrumb every millimeter. If you drop a breadcrumb every millimeter, it's going to give a much more precise picture of what you actually did, but it's also going to take forever. As evidenced, you can see, this is taking forever. But you can tell, maybe you can tell, it's going to be a pretty precise graph. Yeah, barely. Yeah, it's going to take a while. And I think I am going to put this thing out of its misery. Well, let's see here. You know what? Why don't we just slide it off to the side, and we'll just kind of see. I don't think there's a prayer will be done by the end of class. We'll just let it do its thing. It is going to freeze for a second while I draw on the screen, but I'll unfreeze it and you can see how much progress it's actually made. All right. So guys, this will be, I don't know, we'll probably sort of finish here. We might do a little bit on the next page, but I want to talk about the derivative here. And I don't think I can say this enough times, so I'll say it some more. Remember, on a polar graph, the x-axis is still the x-axis. And the y-axis is still the y-axis. And there's still grid lines there. We just typically don't draw them. We usually draw little circles. You can get the x-axis and y-axis is still there. The grid lines technically are still there. And so when I ask you to find the slope and or the equation of a tangent line, it really doesn't matter if it's a parametric graph, a polar graph, or the classic y in terms of x, or some implicit differentiation kind of a equation. Whatever form the equation is that you're dealing with, the slope of the tangent line is always dy dx. It's never dr dt or dr d theta or dy dt or any of those other variables we talked about. The slope of the tangent line is always the tangent line of the tangent. Okay? And so if we're going to be doing something like that, we need to have some y's and x's in there, one way or the other. So I want you to remember, let's do it like this. I'll kind of build this out with parametric stuff that we've talked about in the past. With parametric, let's go back in time a little bit. I gave you, we talked about a very specific way of finding dy dx. Do you remember? Dy dx equals something over something else. Okay, so Josiah is going straight to the polar, and I think he's made a good connection. So Josiah is saying that dy dx would be equal to dy d theta over dx d theta. He's right. So remember in parametric it was dy dt over dx dt, because theta kind of functions as our t with these polar graphs. Theta will be in place of it, if that makes sense. Okay. So then we think, great. If all we have to do is find dy d theta and dx d theta, we'll find their derivatives and we're done, right? It's make a fraction out of it and it's over with. The only problem is if you think back to all the graphs we've done over the last couple of classes, haven't more or less all the graphs been some, 2 plus 3 cosine of theta. It's been r equals this and r equals that, and we got the theta in there, and yes, Jaden, it's a problem. So does anybody have any idea about how I could connect or convert Oh, the conversions. What are they?
X equals R cosecond of Y equals R second.
Yes, Colin, in rapid-fire fashion, has correctly stated those. So these are going to be super useful for us when we think of finding this derivative. So x is equal to r cosine theta, y is equal to r sine theta. So I'm gonna adapt these slightly. You are correct. But based on what we've been doing, would you guys agree with me that r is usually some function in terms of theta? So I'm going to rewrite this. This will be a little bit less. This will be a little more useful notation, I suppose. So I'm going to instead say my conversion will be x is equal to f of theta cosine theta. Y is equal to f of theta sine theta. So all I'm doing is I'm acknowledging that in all likelihood r is some function in terms of theta. Essentially, if r is not a function in terms of theta, if r is just a constant, it's just a circle. So we're going to be dealing with non-circles here, I suppose. Okay, so a key to helping us with this, what is the mathematical operation happening between the f of theta and the cosine or sine of theta? It's multiplication. So when I go to find some derivatives, what is going to be involved? It's going to have to be a product rule. So here we go. Using Josiah's idea and then these conversion table or these conversion equations that we've got going on here, I'm going to write this out. So dy dx will equal, first of all, dy d theta. It's going to be your product rule, right? So 1d2 plus 2d1. So it's going to be f of theta times cosine of theta. So there's 1d2 plus 2. And then d1 would just be f prime of theta. If you left it in terms of r, you could just put r prime right there if you want. Obviously, similar idea. So that's your numerator. And then, of course, your denominator is dx d theta. So again, it's a product rule. So dx d theta, 1, and then d2 is negative sine of theta, plus 2. d1. Okay, so I show you this simply for experience. If you are a master of memorization and you say, I'll just memorize that thing and plug stuff in where they go, you are more than welcome to do that. You will not find me doing that. You will find me doing a quick conversion and then a couple of product rules to get to where I want to go. As we start doing some examples, we'll do those tomorrow. But I just wanted to show you this. I also do want to mention this. I know you guys are math veterans, but nevertheless, I think it's worth saying stuff like this is strictly prohibited. Correct? We giggle and we laugh. Yet those things happen from time to time. Like, Mr. Anderson, why would I even bother writing those things out? Because don't they just cancel anyways? No, they don't. And of course, you can see there's a wide variety of other tempting offers as far as what might cancel, none of which actually do. So please don't. Okay, let's see here. How you feeling? Again, I hope that our experience with parametric helps here, simply because when we did all those parametric derivatives, I'm sure you noticed that it was dy dx equals blah, 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 t. Right? Like dy dx was in terms of t instead of in terms of x. And of course, here you can see in a similar fashion, dy dx is in terms of theta, not x or t or whatever else. So I want you to make sure that you're comfortable with that. So if I was going to be finding the slope of the tangent line at some value of theta, I would write this. And again, sometimes this is uncomfortable for people. I want you to get used to it. We would say dy dx evaluated at theta equals pi over 3. Right? Not at x equals anything or t equals anything, since dy dx has input theta, you'd say evaluated at theta equals whatever. Can you, based on something like that, can you see how your unit circle skills could be tested here? Because depending on what f of theta and f prime of theta are, those could have trig functions in there. And obviously there's already cosines and sines in there. And God forbid you do a question like Dylan made up and there's ln's and tangents too, and e's. It's going to be tough. I don't think I would do that. It just take forever. Anyways. Okay, so guys, can you tell that I'm trying to go slow and just making sure that we're all good? Tomorrow we'll continue on with calculus. We'll do a couple of tangent line type activities. We'll get into area next week, okay? Hey, let's check on the progress. That's all it's done. Right there. Hey, have a wonderful rest of your day. See you guys tomorrow. It's unfrozen. That's as far as it got. It's very slow.
If we come back tomorrow, do you think it'll be done?
Yeah. It'd be done by the end of the day. Probably by 3 p.m. I don't know if I'm going to run it the whole time. I'm probably going to use it in AB. So. Oh man.
You could graph like that.